Hello, in this video we're going to discuss about eigenvalues and eigenvectors. As a review, we have learned that a matrix A has is consists of column vectors, for example like that. And then we've in linear spaces, in the introduction to linear spaces, we have learned that if these column vectors, let's say are V1, V2, and let's say V3, and all of these vectors are linearly independent with each other, then these vectors has an ability to transforms certain x, okay, certain x into another point in the space, and this point and this one, let's say, could be any point on this space, and that is the solution for ax is equal to b. So we have learned that matrix A transforms x into a position b, and remember that b could be anywhere on this space. It could be anywhere there. It could be here as well. So it could be anywhere on this space, anywhere there. Alright? Now, and then we have said that there is also a possibility that there are some values, or there are some x that can be transformed by v1, v2, v3 going to the origin. Let's say this is our origin. So there is a possibility that there are some x's that could be transformed by these vectors into this origin. And that scenario happens if you have ax is equal to 0. Meaning A transforms x to the origin, to the null space. Alright? Or what is the set of all x that can be transformed by v1, v2, v3 into the origin. So just try to imagine, just for you to have an intuitive idea of that. Imagine in the basketball, alright? So let's say that the ring, I really don't know how to draw, but it's upside down there. So let's say that this is the ring, okay? That is the ring. And let's say that this one is the origin, okay? That is the origin, alright? And these are the players. This is the player 1, let's say player 2, let's say player 3, and this is, let's say, player 4, right? That is player 4. And among these people, only, for example, only player 3, or not only, but player 3, if he's in this position, if he can shoot it, if you pass the ball to him, he can actually shoot it into the origin. So, for example, this one can also shoot, has an ability to shoot the ball as well into the origin. So what is the null space then? The null space is that imagine that these are all different positions of those players, different positions of those x. In which positions, or in whose player among these four can throw the ball into the origin. So in this case, it's the player 1 and the player 3. So they can actually shoot the ball. But any of the player can touch the ball. Any of the player can touch actually the ball. And any of the player has an ability to shoot. It's just like, it could be like when they goal it. When they goal, for example, in this position 4, when they goal it, alright, there is a possibility that is not being it cannot pass it, or it cannot shoot it into the origin, or it cannot shoot it into the goal. So in that case, this player number 4 has no ability to go and shoot this one to the origin. So that is the null space. The null space is the set of all these players who can shoot the ball into the origin, right? Now, but this is something good because this player 4 can actually pass the ball to player 2. The player 4 can pass the ball to player 1. Alright? So meaning it could be like matrix A that also transforms this player and they gonna go to another position B. So meaning this one, the matrix, imagine that the matrix is like an energy because they have an ability to move, okay? The matrix or the energy of this player 4 has an ability to pass the ball to player 2. So meaning this B can be player 2, this B can be player 1, this B can be player 3. So meaning player number 4 can pass it to player 1, player 2, player 3. But this player number 4 cannot pass it to or cannot shoot the ball into the origin, right? So something like that. Now, so therefore, what we can that is the intuitive concept of AX is equal to B. Now, however, in eigenvalues and eigenvector, it's a different thing. In eigenvalues, it only tells you that if A will transforms the vector x, we are interested to set of x that is not the origin, not in any point, but to vectors that will go into similar direction as the initial one. So meaning, if this is your vector x, and this vector x will be transformed by A. This vector x will be transformed by A. What we're interested is that the final or the output must be within this line. Must be the same direction of this. So that's the meaning of that. If that is, for example, your x, if you get 2 times of that, if you get 2 times of that length, so you have that one. So that is 2 of your vector x. If you have, for example, 3 times of that length, then you have 3 times of vector x. So meaning, if A will transforms vector x, okay, it might go, or the one that we're interested in, it might go to 2 vector x, or it might go to 3 vector x, or it might go to 1/2 vector x. But I won't say 1/2 vector x. So imagine if that is your x, 1 of vector x means it's actually half here, like that. But still in the same direction, still on the same line. It's just like it's only half of the magnitude of that vector x. Or it could be on the opposite direction. It could go this way as well. Alright? Here we are just saying that the lambda is negative, but actually it's still the same direction. It is within the line. Right? So that is the concept of eigenvalues and eigenvectors. We are looking, I'll just write it down here. We are looking for the set of x, the set of vector x that can be transformed. Or my handwriting isn't that good. Set of x that can be transformed by the column vectors, by the vectors that contains in A into the same direction, into the same direction as x. Okay, like that. So that is the concept of the eigenvalues and the eigenvectors. Okay, so again, the null space is that we're looking for the set of all x that transform by A into the origin. All right, let's try to look at this first. This one means the set of all x that can be transformed by A and will be moved to other point B, and the P could be anywhere on the space. This one means the set of all x that can be transformed by A into the origin. Okay? This one means the set of all x that when transformed by A, it will be on the same direction as x. It will not go out of that line. It will just stay on that line. Alright? So that is the one that what we're looking for. Now, the question is that when does the eigenvalues and eigenvectors exist? When it will exist. In which instance where it's possible to happen. So let's try to go back to the definition that I gave you, that ax is equal to lambda x, right? The characteristic of A should the A must be this A must be non-singular. The word sounds highfalutin, but when you say non-singular, it means that the column vectors of A are all independent. Okay? The column vectors of A are all independent. That's the meaning of that. The column vectors of A are all independent. Or it means if we say that the column vectors are all independent with each other, in terms of determinants, we can say that the determinants of A must be non-zero. Okay? So the determinants of A must be non-zero. Now, but by inspection, how could we check whether, hey, these column vectors, this matrix has a column vectors of all independent vectors. This matrix has a determinant of not equal to 0. How can we check that one? Well, if we use the row echelon of the matrix, if we take the row echelon of the matrix, you could say that there are no rows. I could say no rows that is completely, okay, that is completely 0. So no rows that contains completely 0, meaning you will never encounter this, like there are all 3 zeros at the bottom, or even in another row, or even in this row. Alright? And by the way, A should be a square matrix. It could be 2 by 2, it could be 3 by 3, it could be 4 by 4. If A is not a square matrix, then there's no eigenvalues for that. Right? So these are the conditions. These are the conditions for the eigenvalues and eigenvectors to exist. A is non-singular. In your examination, the key word, they're using the word non-singular. However, what does it mean is that the column vectors of A are all independent vectors. So meaning all the column vectors of A are independent. The determinant of A must be non-zero. That is the implication of that. Or by inspection, we can say we can easily see whether the determinant is non-zero or whether the A is non-singular if there are no rows that is completely 0. Alright? Now let's proceed on how to solve it. So you have there Ax is equal to lambda of your vector x. So you have there Ax minus lambda of your vector x is equal to 0. However, this and this, if you want to subtract, you cannot subtract this because this is a matrix while this one is a real number. So therefore, what you need to do is to multiply this one by its identity element, which is equal to 0. Again, remember identity sub n. If, for example, your A is a 3 by 3 matrix, therefore your identity must be a 3 by 3 matrix. And what is that identity matrix? It's 1, 0, 0, 0, 1, 0, 0, 0, 1. Alright? So, and by factoring out vector x, it's going to be A minus lambda I, vector x is equal to 0. Now, take a look that now it goes back to the concept of the null space. Look at that one. It goes back to the concept of the null space. So how shall we find the eigenvalues? And how shall we find the eigenvectors of x? So what we're going to do is that we need to find first the eigenvalues. So we have there A minus lambda I. For you to be able to find the eigenvalues, you actually need to take the determinants of that is equal to 0. Alright? Now, so I'm gonna cut this video here for a while, but this is the process. This is the process on how to find the eigenvalues and eigenvectors. See you on the next video. Thank you.